So continuing with this pre-quantum time period, today I'm going to talk about the photoelectric effect. So the last three videos we went through the black body effect, black body spectrum, and I just wanted to give you a quick overview of what we did. We said that a black body is an object that doesn't reflect. And one way to make a nice black body is with a cavity, because any light that comes in is probably not going to make it back out of the cavity. The only light that's going to make it out is the one that's generated in here. It's just emitting. And so here you got this thing is a hot object right here, and the atoms are jiggling around. They're making radiation. Some of that radiation leaves the hole. You have a detector here that measures that radiation. And what does it measure? It measures the power, how much energy per second is going in there, between F and F plus DF, within a little infinitesimal frequency range. Now, the answer, when they measure this, looks something like this. I'm plotting it out versus wavelength, but we know wavelength times the frequency is the speed of light right here. And so you get a curve that looks like this. The problem is they could not derive this curve. What they could get is they could get the area under this curve. The area is sigma t to the fourth power, where sigma was the Stefan-Boltzmann constant. And this peak wavelength times the temperature was a constant. So at higher temperatures, this moved this way since you're plotting it out versus wavelength. And so if you can figure out where the peak is, I guess you could figure out what the temperature of the object is. So what Raleigh and Jeans tried to do is to try to derive that, they turned it into a power per unit volume. And we noticed that it took a factor of C over 4 in there. And then they took this power per unit volume in a little frequency range and turned it into the number of oscillators per volume times the average energy. Now we're back to an energy per volume. Okay, this term, when we just added up all the possible frequencies you could get, came out to be this. L, we just made it a cube, so it was just L cubed the volume. And then when we tried to calculate the average energy, this is the way we calculated the average energy, and this thing came out to be KT. Well, when you plug KT up into here and you plot it out, it looks like this right here. It certainly doesn't come back down. They called this the ultraviolet catastrophe because over here you're in the ultraviolet part of the spectrum. So what Planck had to do is he said, I'm going to come back to here and I'm going to make it so that this thing goes to 0 at high energies. This is higher energy over here. So at high energy, I want this thing to curve back down rather than take off this way. So I want this integral to go to 0 at large frequencies. Well, he said, why don't we let E equal HF or 2HF discrete, not a continuous quantity. Up here it's continuous. And you can see at high frequencies, if this is the size of your HFs, if you tried to calculate the area now, is you go over to there, then you go up to here, and you'll notice that this area is much smaller than my original area. If HF is even bigger and I come all the way out to here, then you're only talking about even a much smaller area. So this is one way you can make the integral go to 0 at high frequencies. And when you do that, when you say that energy is quantized and sum it up here, so now it's a sum rather than an integral, we got this, right? And where H is 6.6 times 10 to the minus 34 joule seconds. It's going to be a fundamental constant. We're going to see it the rest of the course. Again, so what he's saying is that all oscillating systems, these electrons or whatever that are jiggling around, these atoms are jiggling, they can only jiggle at these frequencies. And it wasn't just atoms, anything that's oscillating, he says, you're limited to these energies. Okay, so that's the black body spectrum. Now we want to go to the photoelectric effect. This was probably around 1900. This is This was, a lot of people worked on the photoelectric effect, a lot of experimentalists. I think there was quite a few Nobel Prizes on this. And Einstein will eventually solve it in 1905. But let's go through the photoelectric effect. What we have is we have two plates, right here, two plates. And we'll hook them up to a battery. So this is kind of like a capacitor, right here. So we'll hook it up to a battery. And we'll also hook it up to a current meter. So let me just put a little A in there for current meter. So here's my voltage source. Voltage source. We'll just call it V. And this is my current meter, and this will measure, we'll call it little I. Now I'm going to make this thing a variable voltage source so I can turn it up, turn it down, turn it negative. So if we just put a little arrow across here, that means it's a variable voltage source. I can turn it up, turn it down. Right. So what I'm going to do now is I'm going to put this section into a vacuum. So maybe I'll put that in a different color. We'll encase this into a vacuum right here. And then I'll put a little window right there. This is a window because I want light to get in. So what are we going to do? We're going to send in some light onto this plate right there. And that light is going to have a certain intensity. We'll call it I naught. And I can vary that too, the brightness. That's just the brightness of the light. Now, what happens when you shine light at a surface right here? Well, what you can get coming off of here are electrons. Little electrons popping off the surface. So they're popping off from the light hitting it. They give those electrons a name. They call them photoelectrons. They're just electrons, but since they're pushed off by these light right here, they call them photoelectrons. Okay, and so what are we going to do with this experiment? Well, what we're going to do is we're going to vary some stuff. What are we going to vary? We can vary the voltage, we can vary the brightness, and we can even vary the frequency of this. All those will vary individually, and we'll see what happens to the current, the charges flow. Because if these electrons make it over to here, it's going to create a current right there. Okay, so what first thing we'll do is we'll just vary the voltage. So we'll plot out the voltage, and this thing will always be the current, because that's always what we're measuring, the little I. Okay. So, just to begin with, let's say we turn this voltage off. So V is 0. Well, this light comes in, these electrons are still going to pop off, right here. Electrons pop off. So I'm going to get some current right here. And these plates are pretty close together, so pretty much all the ones that popped off are going to come over to this side. So we get a certain amount of current right there. So now let's turn up the voltage so that this becomes more positive and this becomes more negative. So now what are we doing? We're pushing them over. Well, do we get any more electrons? No. We've already gotten all the ones that popped off. All they might do is go a little bit faster by the time they get there. But there's not going to be any more electrons right here because we've already knocked them off. We can't knock them off this with just this voltage right here. So when you increase the voltage, it just stays the same right here. And so we're putting some certain brightness into there. Okay, so now what happens when we flip the polarity of the battery? So now that this one is now negative and that one's positive. So if the one side, let me just draw it here. If this is now the negative side, and this is now the positive side, then these electrons right here, even though they're moving that way originally, the force on them is back this way, right here. Remember, because the electric field is this way, and electrons are negatively charged, so they always go against the field. So there's a force on them. The force is actually in that direction. And if we wanted to calculate the work on this, right, due to this force, the work is just force times the distance, where this distance is right there, d. It's a constant force, so we don't have to integrate or anything. It's just force times d. And we know what the force is on, there's an electric field in here, and it's just Q times E times D. But from electromagnetism, E times the distance is the voltage. So it's just Q times the voltage. That's what the force is. And my Q is actually a minus E. So that's minus E, the charge of an electron, times the voltage. Well, we know that's the only force on the object, so that's the total work. And we know the total work is the change in kinetic. So that's equal to the final kinetic, the kinetic when you're over here, minus the initial kinetic. So here was initial, here is the final. So it's the final, Kf minus K naught. Well, I want to know what voltage do I need to where I just stop them. That is, I'm going to turn off all the current, right? That would mean that the final kinetic is 0. They stopped before they got to there. So this will go to 0. And these guys must have been the fastest ones because they were the last ones to make it there. So we could even call this the maximum initial kinetic energy, the maximum kinetic energy. And we could even call this V naught, the voltage it took to stop them. So we could say, cancel the two minuses, E times V naught equals the maximum kinetic. So when I turn this battery around, or whatever, this voltage source, and go the other way, what this thing's going to do is it's going to come down and eventually go to 0. I've stopped all the current. That occurs right at that V naught, which is, and these guys would have the maximum kinetic energy. They were the last ones to stop. So this is the kinetic max right there, these electrons. Okay. Well, let's go ahead and let's say we come over here and we double the intensity. Well, if we double the intensity, we're going to get twice as much current. Well, you get twice the brightness. So over here, if I double the intensity, I would double. If I double the intensity, I double the current. I'm still with 0 volts. If I turn up the voltage one way, I don't get any more. I've already collect all the ones that pop off. If I turn the battery around and go the negative way, this thing actually comes down to the same spot. This is 2I naught. If I triple it, go to 3 times the intensity, make it 3 times brighter, this will just come up to here, and it'll still just come down to the same spot. This is 3I naught. Well, this is kind of strange because what this is saying is that the speed of these, because remember this is the maximum kinetic energy of the electrons, the kinetic energy of the electrons is independent of the brightness, which is certainly not classical. Classically, you'd think if you made it brighter, you'd kick them off faster. So what can we say? This is statement one right here. We can say the kinetic energy is independent of the brightness. Well, let's just say doesn't depend on the brightness. Doesn't depend on brightness. This is not classical. Classically, you would think that the kinetic does depend on the brightness. So this is non-classical. Non-classical. Okay, what else? Suppose we were to plot out the intensity on this side, intensity I naught right here, or just, let's just say intensity. Versus the current, little I, right here. Well, and this is only for positive voltages, only when you're moving. You can see right here at I naught, you have a certain amount of current. If I double I naught, I double the current. If I triple I naught, I triple the current. Well, that just looks like Y equal X. So this is just going to go off like this. Right there. Okay, and that makes some sense. If I double the brightness, I get double the current. Triple the brightness, triple the current. That is classical. So this is a classical result. Classical result. Okay, that makes some sense right there. Well, what if we look at, first of all, how much time it takes for these electrons to pop off after we put the light on? We haven't looked at that. So suppose here's the sheet right here. Here's your plate. I'm just going to draw it like this instead of drawing it upright. Let's just say that this sheet is made out of potassium. Why? Because I know how much energy it takes to kick off an electron off of potassium. To kick one electron off of potassium, it takes about 2.22 eV to free him up. So I need to make sure that has that much. I also know that the atom, when we'll put a real weak intensity here, we'll put some intensity light on it. Let's just put some I naught. How about just 1/100th of a watt, 10 to the minus 2 watts per square meter. Remember, 1/100th of a watt is pretty dim right there. 1/100th of 1 watt of a bulb right here. Okay, so this is a pretty dim light right here. And now you notice this, each atom, the size of an atom here, the radius is about an angstrom. It's about the radius of each one is about 10 to the minus 10 meters. That's the radius of each atom right here. So if I just want to know how much of that power, how much power is going to this at one atom right there. Well, we know there's this much power going to the whole meter squared. How much is going to that? Well, you just multiply this times that area. So the power going to one atom, power to one atom, it's just going to be that 10 to the minus 2 watts per square meter times the area. Area of a circle is just pi r squared. Pi times 10 to the minus 10 squared, pi r squared, meter squared. Okay, so you notice we're just in watts. So there's how much wattage is going into just that one atom. Remember, power is energy per time. So this is how much energy is going in per second. So if we wanted to get the energy in 2 seconds, you'd multiply it by 2. If you wanted the energy in 3 seconds, it'd be 3. Or the energy in any amount of time, if I just multiply that by t, that's the energy in that much time. So if we'll just multiply this by t, that's, well, pi, that's just 3.14. And then that's 10 to the minus 22. Make 10 to the minus 20 and 2 more times 10 to the minus 22 t. So there's how much energy is going into that one atom as a function of time. Now I just need to know, when does he get enough? When he gets 2.2 eV, he'll kick off his electron. So why don't we just set that equal to 2.22 eV? Find out what time it is. Well, I have to change the unit. Why? Because this is in joules and that's in eV. So I'm going to move this, multiply this by 1.6 times 10 to the minus 19. That's how many joules per eV. So the EVs are gone. This is in joules. So all we have to do is just divide out this number right here, and so we end up with the time is 2.22 times 1.6 times 10 to the minus 19 divided by 3.14. 14 times 10 to the minus 22. This would be in seconds. And this thing came out to be, about, I think I got 1.13. Well, if you turned it into minutes, this was about 19 minutes, 20 minutes, 20 minutes. It seems like a long time before I'm going to get electrons popping up. Well, if you do this, electrons pop off instantaneous, nanoseconds. It doesn't take them 19 minutes to pop off. So this is definitely non-classical, the time it takes for them to come off. So this is also non-classical. It's kind of strange. It's almost like all the ocean waves hitting a beach, and all of a sudden, all that energy of that big wave goes into one shell and kicks the shell out like a cannon. That's not the way light should work when it hits a surface. All that energy doesn't just go into one electron and kick it off. Right here. So, okay, so there was another problem. If we come back, and now we'll change the frequency of the light. So what we'll do here is we'll still change the voltage, but first, instead of doing it at a specific intensity, we'll do it at a specific frequency. If we do it at a specific frequency, we're going to get a pattern just like this, just like we got for that one. At a specific frequency, it's going to come down to here. So let's just call this frequency 1 right there. Again, this is current along here versus the voltage. Well, let's double or at least just make the frequency larger. If we make the frequency larger, we don't get any more current right here. It's right here. This is, say, F2, where F2 is bigger than F1. But when it gets over to here, what we get is we get it over to here. So F2 comes down to here. And if we put in, say, a third, say F3, F3 would just come out even further right here. So this is F3, the green one was F2, the red one was F1, where F3 was greater than F2, which was greater than F1. So remember, these were the speed of the electrons as they were shot off right here. So it looks like the kinetic energy here, kinetic energy of the electrons, depends on the frequency. Well, this is totally non-classical too. Why should it depend on the frequency? So this is also non-classical. And if we were to plot out this point, this maximum kinetic energy right here, or the stopping voltage, it's the same thing. We'll call it the kinetic max as a function of frequency. You notice the higher the frequency, the higher the kinetic energy is. We actually get, so this is versus the frequency, we get something that looks like this right here, a straight line. And the slope of this line, is actually equal to h. The same h, Planck's constant, that we got for the black body. What the heck does this have to do with the black body spectrum? We might also ask, what is this point right there? Well, if you turn down the frequency enough, then even 0 volts, you won't get any. You at least need this frequency to even kick off any electrons. So, okay, well, so this was all of our problems right here. And so now we're going to have to figure out, how do we solve this? And so on the next lecture, we'll see how Einstein solved this problem. Okay.